Proton NMR, 1. Why is it 1 hydrogen rather than 2 hydrogen?
Because
it's an odd number of nucleons. Fantastic. Okay, number of peaks, same with carbon-13 NMR. The number of peaks tells us the number of different or unique hydrogen environments that the hydrogens are in. Hydrogen atoms are involved in the same type of bond, are in equivalent positions in a molecule, will absorb the same frequency and hence produce 1 peak on the NMR spectra. It's another way of saying, right, symmetry, same environment. So in propanone, these hydrogens, well, all 3 are chemically equivalent, yeah, because they're all coming off the same carbon. These 3 are chemically equivalent to those 3 because of the symmetry through that bond, through that atom, right? So that tells me I've got 1 different environment, yeah? And appears as a singlet. We'll talk about splitting patterns in a moment. Peak area ratio tells us the ratio of the number of hydrogen atoms in each of those environments. The chemical shift tells us the nature of the environment, right? And the splitting pattern tells us what environment is nearby to the environment we're looking at, okay? So 4 bits of information we can tell. The number of peaks is the number of unique environments. The chemical shift tells us something about the nature of the environment. The splitting pattern tells us what's next to that environment, right? And then the peak area ratio tells us the relative ratio of the number of hydrogens in that environment. So in this example, dimethoxymethane, not something I'd expect you to know, but if I was to look at this structure, we can see the symmetry in the middle, 2 different hydrogen environments. Yeah. I can see I've got 2 hydrogens in that environment. I've got 6 hydrogens in those environments. So I would expect the peak area ratio of 1 to 3. Yeah? So 2 to 6 is the same as 1 to 3. So we would expect this CH2 here, right, as a smaller area than the area of that one. TMS is 0, we sort of ignore that. Yeah, makes sense? With me so far? Thumbs up, thumbs down, thumbs here. Oh, chemical shift tells us the nature of the environment, and it's in your data book. Yeah? Cool? More about the area, not about the height. Yep. It'll be given to you. It will be written above, and I'll have 2 is 2, 3 above the peak. Okay, chemical shifts in proton NMR. Right, and we'll go through some examples of those. All right, let's look at some simple examples. Ethane. We've seen ethane before, haven't we? Did I have ethane here? I did have ethane here. So there is my carbon-13 NMR. Should be that one. Please hold. Please hold. Ethane. So here's my carbon-13 NMR of ethane. And here's my proton NMR of ethane. TMS is at 0. And anything less than 1 will be our CH3 environment. Yeah? Nothing that exciting. Yeah, we'd see a large peak at 15 and a smaller peak at 60 in our mass spec, and we wouldn't see anything above 1500 except our around 3000, our single peak in our IR spectra. So starting to put all of these pieces together. Yeah. Now, if I look at, say, chloromethane, notice how that chlorine influences, the presence of that chlorine influences the downfield, the chemical shift of the proton NMR spectra. So we can see that that peak corresponding to this hydrogen environment is further downfield than a standard CH3. Okay? Let's go. I'll talk about peak area ratio in a moment. Let's just look at the different hydrogen environments, not looking at splitting patterns just yet. So propane, 2 hydrogen environments, TMS, 1, 2, 3, up to 10. CH3 attached to an alkyl group, less than 1. There's my RCH3. Right, if I look back to my table from your best friends in chem, right, an RCH2R will lead a peak somewhere between 1.3 and 1.4. So there's our RCH2R, right? I'll talk about splitting patterns later. So there's our proton NMR for propane. Now let's consider propan-1-ol. I actually have 4 hydrogen environments. There's 1, there's 2, 3, and 4, right? So we're not just considering hydrogens attached to a carbon, but other hydrogens as well. So we've got our peak for TMS. We have a CH3, so something less than 1, RCH3. We've got a CH2, right? CH2 is between 1 and 2. There's our RCH2R. I've got a CH2 attached to an OH. So that there is here. So we expect something between 3.3 and 4.5. 1, 2, 3. So 4. So expecting something around there is RCH2OH. And then lastly, I've got the alcohol H is somewhere between 1 and 6, so that could fall anywhere within that range. Let's just say in this circumstance, it appears at 5, just as an example. I don't know where exactly, O to H. Okay, so 4 peaks on our proton NMR. Yeah, if I was to guess where that was. Does that make sense so far? Propan-2-ol, right? We can see it only has 1, 2, because that's equivalent to this side. Yeah, 3 environments. TMS. I've got a CH3 less than 1. I have a CH, right? So that's a bit different. My R3CH is 1.5. Right, so it's slightly higher than my normal CH2. So that's my CH, R3. This is my RCH3. And then I've got my alcohol. That will be somewhere else. Three, 4, 5, 6. That's my R, O to H. Cool? So we can see we've got 3 peaks rather than 4. Splitting pattern will also be different, and we'll talk about that later. Carboxylic acid. How many different environments can we find? 3. 1, 2, 3. Where will they be? Look at your special friend. Right, we're going to see 1 less than 1, corresponding to our CH3. Yeah? CH2, where will that be? Right, 1.3, 1.4. Yep. And where will my H on my carboxyl group be? No, that's alcohol. It's not an O to H, right? So O to H here. Where was that? Between 1 and 6 is the H in an alcohol. Here's my carboxyl hydrogen between 9 and 13. So it's way up here. Yeah? CH2, CH3, TMS. Okay, happy so far? All right, so we're looking at number of peaks, number of different environments, and where those peaks occur. Right, let's talk peak area ratio. So if I was to look at the, I'll go through 2 examples here. Okay, in chloroethanoic acid, right? In chloroethanoic acid, I've got 2 hydrogen environments. One of them I've got 2 hydrogens, one of them I have 1. So I have a 2 to 1 or a 1 to 2 ratio. Yeah, depending on how I look at it. 11.2 corresponds quite strongly to that carboxyl hydrogen. So that would be a 1, right? And the chlorine makes this further downfield. So the peak at 4.1 corresponds to that hydrogen environment there. Make sense? And that would be a peak area of 2. Yes? Cool. All right, if I look at methyl propanoate, right, we could draw that structure. I might even do that. Methyl. So we've got an ester, propanoate. Well, let's break this down. What would the IR spectra of that look like? What would the IR spectra of that look like? Well, there's not an ester peak as such. It's the C double bond O. Yep. Not going to have an alcohol. No. No alcohol, no broad stretch are up above 3,000. Single peak at 3,000 for C to H, right? And that strong peak around 1,700 for the C double bond O. So we're talking IR. Nice little recap. We do have a C to O stretch, but remember that's in the background in the fingerprint region, right? What would the carbon-13 look like? Or tell me some of the details of carbon-13. Ollie, what would you see? Ollie, what would you see? Yeah, in carbon-13, tell me one thing that you could see on a carbon-13 NMR. Nothing to do with protons. Carbon-13 NMR, tell me one thing that you would see. Yeah, so you might see a peak corresponding to here. Yeah. What's a simpler bit of information that you could see? How many peaks would I see on carbon-13? 4, right? There are 4 different carbon environments. Yes, these are CH3s, but they're not equivalent. Yeah, because this one is closer to the ester functional group than this one. So you're going to have 2 separate peaks. Make sense? Then that's still not symmetrical because this is single bonded to the oxygen and there's no oxygen joining those 2 carbons. Which it won't. It'll only go up to about C7, C8 at most for what you will get. Yeah. Well, look. You've got 2 CH3 environments, just means you're going to have 2 peaks less than 1, or 2 peaks between 8 and 25. Yeah? So you're just going to see more peaks between there, but each one will be slightly different than the other. And the reason is like, this being closer to an oxygen will make it closer to the 25. This being closer to an alkyl chain will make it closer to the 8. Yeah? ish.